So we have seen how these problems can be addressed, and you can find out the maximum likelihood estimator for the population parameters in each of these cases. Now, MLE is very important and essential for us because it has very nice properties and it helps us to tackle situations which cannot be done using the method of moments estimator method. So here the first situation is MLE can deal with, or it can provide you an estimator even if you have a restricted range for the parameter. Suppose you are taking a random sample from Poisson with parameter lambda. We know that lambda is always greater than 0, right? In general, that lambda is greater than 0. However, if in case it is restricted, that it is greater than 0, but it is also less than equal to 4, then in that case, how do you find the MLE for this, right? And such cases might arise in your real life, because we may not always be interested in dealing with the entire parameter space that lambda is greater than 0, but rather we want to restrict it. Here in this case, it would be restricted from 0 to 4, right? So in that case also, how you can find the updated MLE? Or if you are having a random sample coming from normal distribution with mean mu and variance as 1, so variance is fixed, mu is you are interested, and we know that mu can vary from -infinity to infinity. Rather, if you restrict it, that mu has to be greater than 2. Mu will be at least 2. In that case, your parameter space that was initially from -infinity to infinity, now it is reduced to 2 to infinity. So in such cases, can you find the MLE for this parameter? And yes, the answer is provided by the maximum likelihood estimator. And now we will answer and address these two examples and see what will be the resulting MLE. So the first example in this case, when we are talking about restricted range, so we have that x1, x2, xn is following Poisson distribution with parameter lambda, where lambda is less than equal to 4. Okay, so lambda naught that is given to you, that is the threshold value, lambda naught is 4 over here. Okay, what is the PMF for Poisson distribution? PMF is probability that x is equal to x, it is e power minus lambda, lambda to the power x over x factorial, where x takes value 0, 1, 2 and so on. Because if you see, so here if x is representing the Poisson distribution, you might consider it as the number of accidents that happen on a particular road. Then x can either be that no accident happens, or it can be 1 and 2 and so on. Okay, so here that is why you have the support as going from 0, 1, 2 and so on. So if you have to find the MLE, what will happen? So the likelihood function for this would be, first of all, product of this from I1 to n, e to the power minus lambda, lambda to the power xi over xi factorial, right? So this would essentially be e to the power minus n lambda, lambda to the power summation xi, and this would be product xi factorial. Okay, this is the likelihood function. So till now we are moving in the same way as we have obtained earlier. We can also take the log here. Okay, so suppose you take log of this. When you are taking log, it could be minus n lambda okay, so this one would be minus n lambda plus summation xi times log lambda, and here it would be minus log of product xi's. Okay, when you differentiate this with respect to lambda, because that is the parameter of interest, it would be minus n plus summation xi over lambda. Now if you look at the behavior of this, if it is, this would be greater than 0 if your lambda over here is less than the sample mean. right? Because lambda, if you see, what is the behavior in this case? So summation xi by lambda is greater than n. So basically it means that summation xi by n is greater than lambda, and this is what basically sample mean is greater than lambda, right? So you have lambda greater than x bar, and the reverse would happen if lambda is greater than x bar. Okay, so in this case, so what is happening is that when your lambda is approaching sample mean, it is increasing function and it will achieve the maximum at the sample mean, and it will decrease as you move ahead. Okay, so if you want to plot it, so you can see that if this is lambda and this is your log of the lambda, right? So here somewhere you have your sample mean, right? So this is your log of L lambda, right? Now what you have in your question is that lambda is less than equal to 4. Okay, so lambda is the rate at which the events occur. So if the rate you are restricting it, that we do not want to consider it for the entire parameter space, the rate is less than 4. Okay, lambda is less than equal to 4. We are essentially looking at lambda less than equal to lambda naught situation, right? So here you have lambda naught. Okay, so you will see that where your lambda naught lies. If lambda naught is greater than x bar, and we are interested in the area lambda less than equal to lambda naught, so it means we are focusing on area. Let me use a different color. So we are focusing on this part, right? In this situation where the maximum is occurring, the maximum is attained at this peak, right, which is basically your sample mean, right? In the other situation, what it can be, if you have this, again, if you plot, this is lambda, it's increasing. Here you have the sample mean, but your lambda naught over here is coming to the left hand side. Lambda naught is less than the sample mean. In this case, this is your log L lambda. Okay, and here your interest would be, because lambda is less than equal to lambda naught, so you will be focusing on this area. Now here where the maximum will be achieved, it will be at this point. Okay, so if you summarize them, what will happen is that lambda hat, that the estimator, it will have two situations. It depends upon where your lambda naught is as compared to the sample mean. So if your sample mean is greater than lambda naught, that is this situation, in this case what will be the MLE? MLE would be lambda naught, because here the maximum is attained at lambda naught only. If x bar is less than equal to lambda naught, that is this situation, here the maximum will be attained at x bar only. Okay, so here you will write x bar, and if you want to summarize it, it is basically minimum of the sample mean and lambda naught. Because here also, if you see, which is minimum, if you consider this case, here the minimum is x bar, because that is less than lambda naught, and in this case lambda naught is the minimum. Okay, so which says that minimum of x bar and lambda naught would be the MLE for your lambda hat. Okay, so if you suppose that if you would not have paid attention to this and you would have considered that lambda naught is greater than, you would have considered that, okay, lambda is greater than 0 and let me calculate the MLE as the usual form that we do, then in that case your MLE would be just x bar. Okay, so you are basically ignoring the fact that lambda has been fixed to be less than lambda naught. You are ignoring this lambda naught, and that is why your answer is x bar and your result would be incorrect. Specifically in situations where lambda naught is less than, because when lambda naught is less than x bar, so your MLE would be lambda naught, it will no longer be x bar here. Okay, so here if suppose lambda naught we have as 4, if the sample mean suppose comes out as 6, right, then minimum of these two would be, minimum of 4 and 6 is 4, right? And 4 is what is your lambda naught. So your estimator is lambda naught. And if you would have gone with the usual procedure, you would have said that MLE is sample mean. That means it is 6. So you can see that how the difference is coming. And that is why it is important to pay attention to the support of this, or you can say the parameter space with which we are working. Okay. So this is about your first situation where you have lambda less than equal to lambda naught, or 4 you have written. And probably this, you can see that it can be considered in the other situation where lambda is greater than 4. Suppose you want to see lambda is greater than 4, then you will also move ahead in the same way, and again you will make a graph of that, and then it would become easy for you to visualize it. Okay. The next example that we had was, if you are drawing a random sample from normal with mean mu and variance 1. And here in this case, we said that, okay, the mean has to be greater than 2. Right? Or you can consider that it can be any situation where normal distribution applies. You can consider that mu is greater than 2. You are not focusing on the entire support. Okay. So in this case, as we have already seen, for normal distribution, the PDF would be sigma is 1. So here the PDF would be 1 over root 2 pi e to the power minus 1 by 2 x minus mu whole square, where x takes value from minus infinity to infinity. If I have to write the likelihood function, now since it is independent of your sigma square, which is fixed as 1, so you just have to write the likelihood function. Here the parameter is only mu. Okay, so it would be 1 over 2 pi raised to the power n by 2 e to the power minus 1 by 2 summation xi minus mu whole square. Fine. Now we need to differentiate it. Log of this, log of L mu would be minus n by 2 log 2 pi minus 1 by 2 summation xi minus mu whole square. Okay. When you differentiate it with respect to mu, what you get is, so here minus 1 by 2 is there. So 2 and minus 1 by 2, let me just write it twice of summation xi minus mu, and here minus would become plus. So this would just be summation xi minus mu, which is nothing but summation xi minus n mu. Right, summation xi minus n mu. Now if you look at the behavior, this would be greater than 0 if mu is less than your x bar. Right, so if mu is less than sample mean, that is summation xi by n, this would be greater than 0, and it would be less than 0 if mu is greater than x bar. Okay, so you have two situations. So let us just draw this and see. So basically this is your mu and this is your normal distribution. So here you have somewhere sample mean. So for first it is increasing and then it starts to decreasing. And here it is log of L mu you have. Okay. Now what you are given in the question is that mu is greater than equal to 2, or you can say that this is mu naught. So we are focusing on the region for mu greater than equal to 2, mu naught. Okay. So now the first situation can be, so let me use this. If mu naught lies to this side, right? If mu naught lies on this side, in this case, we are focusing on that area where mu is greater than equal to mu naught. So which means we are basically focusing on this side, right? And in this region, what will be your estimator in this case? Maximum is occurring at this point, right? So mu naught will be your MLE in this case. The other situation can be when you have let us redraw this. Here is mu, this is x bar, and here mu naught is present, right? Okay, now again you have to look at mu greater than equal to mu naught. So it means you are focusing on this region, right? And here the maximum is occurring at this point. Okay, so if you want to summarize this, what will be your estimator for mu? It would be mu hat would be depending upon whether x bar is less than mu naught or x bar is greater than equal to mu naught. When x bar is greater, in this case, right, x bar is greater than mu naught, so the sample mean would be the answer. And if x bar is if it is less than mu naught, if x bar is less than mu naught, so it means mu naught will be the answer, sorry. So here, if x bar is less than mu naught, so mu naught is the answer to this. Okay, and in the other case, sample mean. So basically we are looking at the maximum of x bar and mu naught. Whichever is maximum, that would be the MLE for mu. Maximum in this case, because here the maximum is x bar, this is bigger than mu naught, and in this case maximum is mu naught. Okay. So again, you can see that if suppose mu naught here is 4 and sample mean x bar comes out as 10 suppose. So in this case, you would compare these two and you would say that you will see whichever is maximum, that would be your estimator. If 10 is the maximum, since in this case, so 10 would be your estimator, otherwise 4 would be there. Okay, whatever value of mu naught, this is just a sample case that where mu naught is 4. Sometimes when you are looking at average income, so mu naught could be that you are looking at those people whose income are greater than 20,000 suppose. So you do not have to consider anything else, you are just going to see whose income mu naught in that case would be your 20,000. Okay, so mu naught can be greater than 20,000 mu naught. So you have to be careful with the support that is given or the parameter space with which you are dealing. So we have seen how to address these situations, and this basically reflects upon the benefit and the usefulness of the maximum likelihood estimation method. In addition, there are few remarks which I would like to add. We have seen that both these methods can give you different answers, as we have seen that when you are taking a random sample from uniform 0 theta, so in the method of movements you got twice of the sample mean, and in MLE you got the largest order statistic, that is x ordered n is the answer. Now it is possible that MLE may not be unique. Okay, and in this case you have that if you have a random sample from uniform theta minus 1 to theta plus 1 where theta is unknown, in that case MLE may not be unique. So we will see that what is the answer to that. And the last one is that it may not even exist at times. Why? If you are considering that x1, x2, xn follows binomial with parameter 1 and p is unknown. So when you say binomial with parameter 1 and p, it means you are talking about Bernoulli distribution with parameter p. Right? Now Bernoulli distribution can only have possibilities as 0 and 1. X can be, the number of success can be either 0 and 1. Now if all the xi's are 0, okay, if all the xi's are 0 or if all the xi's are 1, the sample mean would be 0. In case all the observations are 0, all the failures you obtain, it would be 0. And if all these all of them are success, then you would get 1. Okay, so we will see these two situations. I will explain it to you. So first remark is already done. So let us consider the second remark, which says that if you are having a random sample from uniform theta minus 1 to theta plus 1, where theta is r. This is the parameter space, right? So in this case, what will be the density? Fx is 1 over b minus a. So here this is your b, a, and this is your b, right? So 1 over this is basically 1 over 2, where x basically lies between theta minus 1 and theta plus 1. Okay. So here you have to calculate the likelihood function. So likelihood function would be 1 over, since it is 1 by 2 for single random variable, it for n such it would be 1 over 2 raised to the power n, and theta here you see that all the xi's, as we have said earlier also, because uniform distribution has the parameter also involved in the support, so you will write that all xi's are there. Instead of that, I can say that x ordered 1 till x ordered n fall between, all the observations are between theta minus 1 and theta plus 1. Okay. Now this is equivalent to saying that if I just say that x ordered 1 is less than x ordered n is less than equal to theta plus 1. Okay. So this is essential, because if the smallest order is greater than theta minus 1 and the largest one is greater than theta plus 1, so it means rest of the observations would lie in between these two, right? So if you simplify this, what will you get is that you will get a range for theta, right? So theta over here would fall between x ordered n minus 1 from here, this side, and the other one would be x ordered 1 plus 1. Okay. So this theta, you see that it is a range of values and it is not a single estimator that you have obtained. Okay. So you can take the average of this as an example, and many other MLEs could be found out. Okay. So this shows that MLEs may not be unique. The next remark that we had was that if you are taking a sample from Bernoulli P, where P takes value between 0 and 1. So we know that Bernoulli, in case of Bernoulli, if x follows Bernoulli distribution, then what happens is that x can take value between 0 and 1, 0 and 1, not between, it is just 0 or 1. Number of success in a single trial can be failure, it means it is 0, and it can be 1. Right. Now suppose you are taking a random sample from this case, it means that if all these xi's are failures, right, in each trial you get, in each time when you are taking this x1, you get all of them as zeros, right? In this case, what will be your MLE? If you recall from the first example, second example of Bernoulli distribution, we obtained that p hat is nothing but x bar. So in this case, what will be your x estimate would be 0. And if all the observations are success, then your x bar would be 1 in this case, right? So here what is happening is the estimator that you are obtaining, that is 0 and 1, estimator takes value 0 and 1, whereas the parameter does not take that value. It is greater than 0 and less than 1. So p is not equal to 0 or p is not equal to 1. So the estimator that you are proposing is not a good fit, because the parameter, population parameter, does not even take that value. Okay. So you have to be careful while you are dealing with such situations. So we have seen different remarks, and last topic of this week is basically the invariance property of MLE. The invariance property of MLE is very useful, because not many times we are not interested in the original parameter, rather we are interested in some function of the parameter, and we are interested to estimate that function of the parameter. So in such situations, we have a very nice property of invariance, which says that if theta hat denotes the MLE of theta, and you have any one-to-one function, that is g theta, then the MLE of this new one-to-one function is going to be g of theta hat. Okay, so let us see how to answer this. So here we are going to talk about invariance of MLE. Invariance of MLE. So let us first write the theorem and then try to see how it can be proved. The theorem says that if theta hat is the MLE of if theta hat is the MLE of theta, you have obtained the MLE of the original parameter, okay, with theta, suppose the parameter space for this is this, and you now define a one-to-one function, that is phi. Suppose we denote this g theta as phi. G is one-to-one function, okay, and phi hat basically would be g theta hat. This would be the MLE of, you have to show that this g theta hat, or you can say that phi hat is the MLE of phi. And let us see that we can consider this parameter space to be capital phi over here, okay. So if theta is the MLE of theta, that is given to us, and we consider a one-to-one function g, then we have to show that this phi hat, or you can say that g theta hat is the MLE of g theta, okay, provided it is a one-to-one function. So let us try to see how we can do that. So here, if phi is basically g theta, then g inverse phi would be theta, okay. So this inverse would be well defined because it is a one-to-one function, and here the likelihood function can also be written as a function of theta only. So if you are writing it, so L star phi over here, if you are using for likelihood function corresponding to phi as L star, so instead of that it would be same as writing g inverse of phi also. So here instead of that we can write L likelihood function of g inverse phi, so that would be the same thing, okay. So instead of that I can also just tell you that it is phi hat also, then also it will be the same thing, g inverse of phi hat. And what is phi hat for you? Phi hat is basically g theta hat, right? Because phi hat would be g theta hat. So g inverse g of theta hat, which is basically L of theta hat. So now let us try to prove the result. In the result, it was given that theta hat is the MLE of theta. Now, if theta hat is the MLE of theta, it means that the likelihood function corresponding to theta hat would be greater than the likelihood function of corresponding to any theta in the parameter space, right? This would be the maximum. So L theta hat would be the largest one. So if I have to show that g theta hat, that is phi hat, this is the MLE of phi equal to g theta, it means I need to show that the likelihood function, that is L star of phi hat, is greater than L star of phi for every phi in the, suppose the parameter space is this, right, capital phi. I have to show this thing basically, right, because if this is the MLE, it is going to be the likelihood function corresponding to this has to be greater than the rest of them, okay. So let us start with the left hand side. So since L star phi hat would be what? So instead of phi hat, we can write, we have shown that L star phi hat is nothing but same over here, L theta hat, right? We have obtained this property, and L theta hat is greater than L theta because it holds for every theta, it has to be greater than that. And now likelihood function corresponding to theta, or it corresponds to phi, it would be the same thing, right, for every phi in this parameter space. So basically what you have proved is that L star phi hat is greater than equal to L star phi, right? And this is what you wanted to show. So whenever you have a one-to-one function, it is easy to see by this result that the MLE would also be transformed to that function, okay. Now this is about one-to-one function. we may not always have a one-to-one function. So we have a very important result which was given by Zehna in 1967, which said that if theta hat is the MLE of theta, then any function, if you have any function, it should not necessarily be a one-to-one function. For any function g theta, this result again would hold true, right? The MLE of g theta would be g theta hat. Okay, so using this, let us try to address the examples over here. So in this case, suppose you have a random sample coming from Poisson distribution with parameter lambda, right? And you have to find the MLE of function of this parameter, not necessarily this, because for lambda, if you just recall, for lambda, the MLE was sample mean, that is x bar. Now what you are asked is, you have to find the MLE for e raised to the power minus lambda. That is a function of the original parameter. And what is e lambda? E raised to power minus lambda. This corresponds to, because in the PMF, if you see, probability that x is equal to x is e raised to power minus lambda, lambda to power x over x factorial. So when x is 0, this basically would be e to power minus lambda. Okay, and this is very important quantity over here, because many times, suppose the shopkeeper or the owner of any office would like to know that how many customers are turning up. So this is basically the number of, suppose xi's in this case is number of customers that visit a cafe from 4 to 5 p.m. right? And if the shop owner knows that no customer is going to come up, that is x1 is 0, then it means in that case he would be able to find out that, okay, if no customer is coming, what is the probability? So he can maybe employ or assign that person to some other task, right? Maybe 4 to 5 p.m. is a rush hour, so we can consider during lunch hour, suppose 1 to 2 p.m., right? So if in that slot, if no customer is coming, then probably they would close it down for lunch period and then they might return back. So this probability is of very much importance, and you are interested to find the estimator for this. You want to estimate this probability, you know, for lambda. So the answer for this would be, since MLE of lambda is sample mean, MLE of e raised to power minus lambda would be simply e raised to the power minus x bar. And this result is possible only because this invariance property of MLE exists. In same way, you can consider this Bernoulli distribution. For Bernoulli, we have already found the MLE, okay, because this is binomial 1p. So the MLE you have to find for PQ, basically P into 1 minus Q, that is the variance, because Bernoulli case, the mean is P and variance is PQ. So here you have to find the MLE for the variance. Since MLE of P is x bar, you would have the MLE of P1 minus P as x bar 1 minus x bar. Okay, so here actually it should not be x, it should be a sample mean. Okay, some random sample x1, x2, xn is coming from Bernoulli. So as we have seen that it comes out as sample mean. So in this case, it would be x bar 1 minus x bar. Okay, so this basically completes your point estimation and theory of this week. So here we learned about what is the major concept behind having a point estimation, what is the concept of point estimation, confidence interval estimation, we will see later on, and hypothesis testing also we will see in the coming weeks. And we saw that if we talk about point estimation, then we have two different methods, method of moments and maximum likelihood estimation. So in this case, in each case we saw different examples, and then we saw that why MLE is very important, because here you have the nice properties of invariance, and we have the MLEs, you can obtain the MLEs even for the restricted range also. So, and also we will see, if you study more into statistics, then you would see that why MLE is such an important estimator, because it would have most of the properties that is desired for a good estimator. Okay, so that is why understanding the concept of MLE is very important. Now in the next class, we will use Python and see that how these two methods can be applied, and how the estimators that you are obtaining over here, that is sample mean or the largest order statistic, or you have obtained n-1 over sample variance, if you calculate this, are they actually very close to your population parameter, because then only you would say that, okay, this is a good estimator for us, right? And based upon that only we are going to see in the next week the property of unbiasedness. Okay, so we will address these one by one. Thank you.